All right, good evening, everybody. I hope everybody's doing well. And what I would like to do is I'd like to start out, as always, with our guest speaker. Today's guest speaker is Christopher Schaefer. Christopher took data structures about a
2 years
year.
ago.
Yeah. Um, and he has recently accepted an offer to be an intern at Amazon next summer. So first of all, congratulations, Chris, on that. And so what I want to be able to do is give Chris an opportunity to talk about his experience as a student and how he worked towards getting that offer from Amazon, and then give you all the opportunity to ask him any questions that you would like afterwards. So Christopher, the floor is yours.
Thanks. Yeah, so I'm a senior. I worked at Amazon last summer. Um, so I guess the things leading up to that big thing is lead code. But you guys are kind of on top of it. I didn't really have this when I was going through the whole process. Just learning data structures was super important. So like, I don't know if you guys are familiar with the process at all, but during it, you'll get an online assessment. And it's basically, they give you like 2 or 3 different leak code problems, kind of like those, and you just have to solve them in the most like efficient way possible. So what you guys are doing now is great for that. Um, you don't just have to memorize a billion problems. Understanding how things work is way more important. So that lets you solve like any kind of problem, because you're probably not going to see the exact same problem. So instead of just the interview, so yeah, I worked at Amazon. I worked in the Amazon retail division. So I worked on, when you go add an item to your cart, those little widgets that say like frequently bought together, or people who bought this bought those. I worked on that team for mobile phones and a couple other small markets like that. So I wrote a tool that helps developers debug that. So I was like part of my experience there. And then, yeah, I was fortunate enough to receive a full-time offer from Amazon. So I will be joining them in August of next year. I'll be moving back out to Seattle after I finish up my degree. So I kind of wanted to leave it mostly open so I can see what kind of questions you guys had, so I can help you all best with what you guys want to know specifically.
Here, I'll get the question started. So when you're talking about preparing for job interviews and you say that it's important to understand what's going on as opposed to just doing the lead code problems, right? So this is something that I kind of hit on with them with a little bit these optional interviews. But in your experience, and of course I know that you can't share the problems that you did or anything like that, but can you explain to them the kind of things that you had to do when you were going through the actual interview problem that would say, all right, instead of the importance of the type of thinking that you were going into when you did the interview, as opposed to just, oh, I'm going to do this problem and do this answer, kind of different than what you would normally do in a test.
Yeah, so going into an interview problem, you don't know what it's going to be about. It's generally going to be kind of vague. So there's multiple ways to go about it. So by having a pretty deep understanding of data structures and more specifically how to apply them, you can see if you want to use um, like like a binary search tree, if you need to use like a hash map, things like that. And by really understanding, you'll be able to apply these situations, because maybe you need like fast insert times, but you don't need to search things really quickly. So you can use like a linked list for those kinds of questions. It's just really about understanding the actual data structure. And then even more than that, recursion is super important. I also interviewed at Microsoft, and basically the only thing they asked me at the final round interview was exclusively recursion problems. So it's not just data structures. You need to know how to use data structures and a bunch of different like programming ideas. And it's not always going to be super obvious on what you should use. So that's why having like a broad understanding rather than just memorizing problems is typically better than um, yeah, just straight memorizing all the problems. Because then you can apply different things in different ways to problems you haven't seen before.
Okay, so we have a question from Chase Brown. So Chase asks, in your experience interviewing, did the interviewer always expect you to find the most efficient solution, or are they more interested in how you break a problem down?
Hands down, they are more interested in how you break a problem down. You don't have to know everything going in. The interviewers want you to do well just as well as you want to do well. I think one of the biggest things you can do when you have an interview is, instead of sitting silent you want to talk through your entire process. So even if you're not going in the right direction, by talking about through your ideas, even if they might be slightly wrong, your interviewer 9 times out of 10 will give you a simple hint or like nudge you in the right direction. And they'll like say, well, have you considered doing this? So always express what you're doing and why you're doing it rather than just like writing code on a board. Because if you just write all the code on the board, the interviewer can't help you, even though they really want to. So yeah, it's definitely how you break a problem down and how you can communicate that. Because like communication in industry is super important. Um, you have to be able to explain your ideas, your thoughts. Like at Amazon, I got a project doc and they just said, okay, here you go, implement this. So I had to come up with like a design and I had to defend it myself, come up with everything like that. So like being able to communicate is something that they're really looking for in these interviews rather than just raw programming ability.
Okay, other questions? Looks like Alvin might have a question. Alvin, do you have a question?
Yeah, I was wondering, so whenever you go to these like bigger tech companies, do they give you really weird behavioral questions? And is there any way that you prepare for those?
So I don't, in my experience, I didn't really have too many behaviorals. They're like the classics, like tell me about yourself, tell me about some of the projects you've done. It's mostly technical from what I've seen. I can speak to Amazon's interview process pretty well. So the whole first stage, it's you don't talk to a soul. There's 3 online assessments. The first one is like compiling errors and stuff like that. Super simple. If you just got to sometimes like symbols are flipped and just doesn't compile to get your code to compile. Second one's the leak code, and the third one's more like the behavioral. It's just like kind of like a simulation game you kind of play. So that one's kind of hard to fake. So I'd say for Amazon specifically, if you're worried about behavioral aspects, this might sound kind of like I'm selling out, but Amazon really, really prides itself on their leadership principles. You can just Google it; it'll pop right up. It's like a list of things that they look for in all their employees and everything that they do. And they recommend that you read all that before you take the third round interview with them, because everything is like based around that. And like it's not just for the interview process. When you're working there, you'll go to meetings, you'll hear it all the time, like ownership, things like that. All leadership principles are super important. So behaviorals that way, I'd focus on those and have examples of how you either demonstrate those or how you could, things like that, specifically for Amazon.
So here's another thing that I think would be very helpful for the students to hear from you. So you have hit on a big and important point about the importance of communication and being able to take a set of descriptions like a tech document and then being able to develop your own project. So the first part that I think would be helpful for them is to hear, how did you use what you learned in data structures to be able to first come up with an original idea, and then when you were trying to adapt to a different, like when you realized that your initial assumptions weren't quite right, how did you use your knowledge of data structures to adapt?
Yeah. So my thing in particular, it was a kind of like a logging system. So I'd have figure out how to use data structures to efficiently store this data while keeping latency super low. So on my original design, I had some pushback from my team, and then I re-implemented it using different design patterns, the same kind of data structure. It was mostly just a couple of arrays, but the design structure was kind of like a singleton almost. But these different data structures, when you have a project where it's like super open-ended, by just having like an understanding, you'll know how to design something not only that just like works functionally, but like meets like the business need of have to be super low latency and all those other things you usually wouldn't think about in a school project. But when you're impacting like thousands or millions of people, like a couple of milliseconds can be the difference between someone in India. I worked in Amazon India, and they don't have the greatest internet speeds there. So we were constantly trying to optimize for speed. So a couple of milliseconds different on someone who is working on their data out there, it wasn't really the fastest. So you had to be able to optimize, and data structures worked was really important to designing these different programs that I had to write to make sure everything worked smoothly.
All right, does anybody have any other questions? All right, well, Chris, thank you for making time for the students, and appreciate it, and wish you all the best of luck once you graduate and go back out to
Alrighty,
Seattle.
thanks guys. Thanks everybody.
All right, so I'm now moved to my share screen here. And so what I'm going to do for this particular lecture is go over two binary search tree interview challenges. So it's kind of convenient that Chris was saying that all his questions at Microsoft were recursion, because both the solution to both of the problems I'm going to discuss today are recursive problems. And here's where you can find all of the code for later on when you want to study. So the first question is called the maximum path sum problem. And the problem states, given a non-empty binary tree, find the maximum path sum. And so the way it is defined is that for the problem, a path is defined as any sequence of nodes from some starting node to any node in the tree along the parent-child connections. The path must contain at least one node and does not need to go through the root. So the do not need to go through the root portion is actually a really important part of what they're trying to nudge you to get the right answer. And so here is the example from LeetCode. Well, one of two examples that they have from LeetCode. So what they mean by this maximum path sum is you take a path from one node to another and then sum up all the values. Now here the answer is 6, and the reason why is because it's going to be 2 plus 1 plus 3. For a more complicated one like this, what we're going to have is, if I were to take a path here, right, this would be 9, so touchscreen is not quite cooperating. So we have 9 plus minus 10 plus 20 plus 15. And then here you have negative 1, and then that's going to be 19. That's going to be 29 plus 30. So that's going to be 34, right? You go this other direction, it's going to be even less. So we would subtract 8. The path from 15 to 20 to 7 is going to be 42, because it's going to be 15 plus 20 plus 7. So this is where they're telling you that you don't have to go through the root in order to be able to obtain the solution. So if we're going to visualize the solution, we have to think of ways that we can break this problem down. If we were trying to just come up with every possible path, that would be the worst case of big O of n squared. We'd want to try to avoid that. So the question is, how can we evaluate everything and come up with a set of sub-solutions? So part of that is this idea I've been hitting over and over again of dynamic programming. We're using previous solutions to develop newer solutions. Prevents you from having to check all the possible paths. And likewise, because we want to try to come up with dynamic programming, we eventually want to use recursion, because recursion will allow us to be able to traverse the tree, and then we want to store intermediate solutions in each of the recursive calls. So for visualizing the solution, we would say that at the bottom nodes, when we have one node each, like the problem stated, well, those paths are just the value of that specific node. So it's 9, 15, and 7. But now if we're going to move up to this next level, we have to consider all of the possible ways in which we could get a solution from these 3 particular nodes. So if we had a full path, this would be 20 plus 15 plus 7 is 42. But let's say that I change this to negative 7. Well, then 20 plus 15 is 35, minus 7 is going to be 28. So the actual path would be just 20 and 15 here for this subtree. Likewise, if I change this to negative 15 and negative 7, then the actual path is just the node 20, because anything else involves subtracting. And then if I did negative 15 and positive 7, well, then the path becomes 27. So here we have three potential scenarios. Scenario one of the values is greater than the sum of all. And then over here we have negative 9 plus 10 plus 42 is 41. So the right path sum is the largest on the right-hand side. And now we have this other scenario with negative values where 7 is the largest path value here, right? So if we had 7, then we'd want to have this value come up, right? But there's an issue here. Let me click through a couple more animations to show. So if I'm going through this here, we could say that the left max path sum is negative 15. And then this particular path on the left is negative 20 and 15, so that's negative 35. The right path is 7. Negative 20 plus 7 is negative 13. So we know that the correct solution is 7 for this subtree. However, if I'm bringing it up, I can't say 20 plus 7. We cannot do that because this is not an actual path. The path would have to include negative 20, which becomes a problem. So we can't just add recursively. So here is how I would approach this particular problem. So the first thing that I have here, zoom in, those are all my tests, is I have a maximum path, and what I'm going to do is I'm going to be at a specific current node. So anywhere we're in the tree, we can have this be a particular subtree, and then we can come up with a set of sub-solutions, and from there we can use that to build towards our final solution, which means we only have to traverse the tree in a pre-order traversal. I have two values that I have called by reference. One I call maximum value, and the other one I call maximum value path. And that is to address this particular scenario where I had 20, negative 20, and 7. And so for here, what I would return is the max value would be 7 coming up here. And then what I'd have is I'd have that negative 15. And what would happen is the largest path coming up would be negative 13 because of the path between negative 20 and 7. And so this allows me to account for a particular scenario. So here I have negative 13 for the path, and then I would have 7 here. And then 20 minus negative 13 is also 7, so it's a tie. But if I made this 25, then this actually becomes beneficial to understand the path because 25 minus 13 is 12, which is actually greater than 7. So at each level, we have to account for all of these different scenarios. So I've done this by keeping track of those two integers with a call by reference. The second thing I've done before we begin anything involving the actual algorithm is what happens when we get to cur node is equal to null. So in this case, the max value is going to be 0 and the max value of the path is going to be 0 because we're just at a null pointer and we haven't added anything to it. So what this is going to allow us to do is pass both of those up as zeros, and this is our base case to be able to build the dynamic solution. So now let's visualize the solution a little further. So I have the max path in red and the max value path in blue. So when I come up, what's going to happen is, sorry, when I clicked a little too fast. So when I come up here to just this particular node, I'm going to have -9 and -9. Likewise, I'll have 15, 15, 7, and 7. So now I have all of these potential scenarios. I have just this path could be 20 plus 7. I have just this path could be 20 plus 15. I have the full thing that's a subpath where it's 20 plus 15 plus 7. And we have to account for all of the possible outcomes. And so the way that I do this is I make my recursive calls. And the way that I do this is I set up a max value for the left and the maximum path value for the left. And then I take the current node's left pointer, and then I pass max value left and max value path left. And then I get those values because they're called by reference. And then I do the same thing to the right. And now when I do this, I'm going to have all of the pieces of information that I need in order to be able to solve this problem. And the way that I do that is with these three additions. So first I have sum of all paths. So that's the scenario where I would have 15, 20, and 7 is equal to cur node data, which in that scenario is 20, plus max value left, which would coming up is 15, plus max value right is 7. Then I have sum of left path is cur node data plus max value left. And then I have sum right path is cur node data plus max value right. So then I have, let's say if I had 20, -15, and 7, then sum of all paths would be 27 minus 15, which is going to be 12. Sum left path is going to be 5. And then sum right path is going to be 27. So from here, now I know that the right path is what I want to represent everything. So now we have to actually make a decision between those three values. And the way that I do this is I use standard max. And standard max is part of the pound include algorithm library in C++. So I have that included here. And you're a little familiar with algorithm. Standard sort uses the quick sort algorithm that you wrote in your creativity challenge 2. So the thing with standard max is it brings in two inputs, and I have three values that I wish to compare. So what I've done is I've done standard max, and then returned that result, and then called standard max again to be able to do 3. And that gives me what I call max value path local. For the max value local, which is not the path, but what I'm trying to propagate up in the event that I have this very large value at the bottom of the tree, I do the same thing, except I compare max value left, max value right, and then in the third input, I use the current node data. So there I would have 20, -15, and 7, for example. This would be 20, because I would have this value being the highest. So now we need to make our decisions. And so the next piece of code is what I have here on the slide. And in the event that I had 20, 15, and 7, then max path would be the greatest of 35, 42, and 27. So that's going to be 42. And then if I had just the values, it's 20, 15, and 7, so that's 20. So if I have a valid path, then my valid path would come here, and 20 is not greater than 42, so we were going to move down here. So let's consider this case first, and then I'll walk through the other case. So here what I'm going to say is I'm going to say the maximum value is actually equal to the path value. That's when I want to pass up. And then set the call by reference for the max value path. So both of them are, in this case, are the same. I want this value to propagate up because I have a valid path as well as the solution. The other case would be, well, what would happen if I had negative 20, negative 15, and 7? Max value would become 7. And then here, for the max value path, based on the previous code, well, I would have negative 13, negative 20, and negative 35. So the greatest of those is negative 13. So this becomes 7 is greater than or equal, greater than negative 13. So now what I do is I set the max value equal to max value local, which is 7. And then this last part, let me erase everything else so it's clear what it is that I'm doing. So this last part, I want to disassociate and say that we have to make a connection, a disconnect in this path. So if I have 20, I had negative 13 and 7, I would want 7 to come up. But in this case, because it's 0, I know that this is not a valid path, and therefore I'd have to consider that result. So now we've overcome that particular challenge. So let me take you through some of the tests that I've done to figure things out. So this particular, what I've done is I have my binary search tree node that I presented in lecture, and then it's node 0, so that's negative 10. Node 1 is 9, and we see that node 0 left becomes the address of node 1, so that's 9. Node 2 is 20, so node 0 right is going to be 20. Then we have node 3 and node 4, so this is 15 and 7. Node 2 left is node address of node 3, and node 2 right is the address of node 4. So this becomes 15 and 7. So here I've built one of those examples. And here I set max value and max value path initially equal to 0. I put them into the function. They're both call by reference. And then what I do at the end, just like I've done before in the recursive calls, I say the maximum path sum, and I call standard max, and then I get either max val or max value path. In the second test, here I have node 0 is 2, node 1 is 1, and node 2 is 3. And so node 0 dot left is the address of 1, so node 0 is 2. And the address of 1 is left, so we're going to make that 1. And node 1 right is 3. And this is the case where we knew that the solution should print out 6. Test 3 is going to be the exact same thing, except now what I have done is I have 10, 9, 20, 15, and negative 7. And so now I've changed the sign of 10 from negative to positive, and I've changed the sign of 7 from positive to negative. And so what's going to happen is our algorithm should correctly determine that the path is 9, 19, 39, 49, 54. That should be our outcome. And now what I'm going to do is I'm going to compile and run the code, but I have this here, and you'll see that we got all the values that we expect. So this compilation is make MaxPathSum. And so in our first test, It printed out 42 as we expected. Our second test printed out 6 as we expected. And then test 3 printed out 54 as we expected. Okay, so before I go to the second question, does anybody have any questions about our approach in the first problem? Check to see if there's any hands up. Awesome. All right, so then let's go on to problem number 2. So this problem is called subtree of another tree. And we are given 2 non-empty binary search trees, S and T. We need to check whether T has the exact same structure and node values with a subtree of S. A subtree of S is a tree consisting of a node in S and all of the node's descendants. The subtree S could be considered a subtree of itself. So let's compare and see what it is that they mean. So here we have the screen capture from LeetCode, and they have this tree, and it's a binary tree, not a binary search tree. So it doesn't necessarily have to be in order. And our solution, it doesn't matter. Well, the approach we're going to use, they don't have to be in order, but you can do it that way. So they have S and T, and the second tree is 4, 1, and 2. And what they want you to be able to do is find this tree and see that somewhere in S, that subtree exists in precisely the exact structure. Okay, so here's the second example. Let me draw this out. And this solution is false, and this helps you kind of pinpoint our approach to the solution. So tree S is going to be 3, 4, 5 is the right child, 1, 2, and 0. And the second tree is going to be 4, 1, and 2. And so the common question is, well, here I have 4, 1, and 2 inside of this tree. So the structures here match. So the question is this a correct answer? Now we see here that it's not, but the question is, well, why? The reason why it's not is because the valid subtree aspect of the problem. It has to have the identical structure, which means 2 here in this tree has 2 null children, whereas in this tree, 2 has a valid non-null child, which means they do not have the same structure. So therefore, they are not identical subtrees. So going back to the phrasing of the question, given 2 non-empty binary trees, check to see whether tree T has the exact same structure and node values with a subtree of S. So we see here that they're kind of putting things in the same way as I've been saying this semester. Structure and node values. So it's data versus structure. So the crucial aspect is when you apply your algorithm, you want to focus on the structure and then just check the actual data nodes when we get there to make sure that they're the same. So let's take an approach and see what we'd want to do. So the first thing we want to see in this particular tree is, well, how do I find where the value is in the tree? So the first thing I need to do is say, well, I know that this tree has a value of 4, which means first I have to figure out if the value of 4 is in the tree in the first place. But it's not good enough to just figure out that the value 4 is in the tree. We have to have a pointer to that specific node. So what we need to do is get the value, and then we need to be able to traverse the initial tree. And then once we find it, return a pointer to that particular node. So we have to create a method that finds that value and returns BST node. And remember, it's data versus structure, so you want to consider genericity in templates, to return that specific value and return the location. And the reason why we need to know the location is so that way we can evaluate the tree after that and to get that result. So what I have done is in the code for the binary search tree that I've provided on the course page, I have written another function. Excuse me, let me hide the meeting controls. And the function is called getNodeAtValue. And this is a private recursive call. And in the public recursive call that I'll show you in a moment, I just pass root and the value that we're looking for. So I'm calling by reference because I want to maintain that if it's a huge piece of data, we only want to pass the pointer, but then I don't want it changed at all, so I'm passing it as constant. The first thing I'm doing in this function is I'm trying to traverse. So the first thing I do is I say if cur pointer is equal to null, return null. The reason I do this is because let's say I'm looking for the value for in this tree. So I have 10, 6, 1, and 7, and 12 over here. So I would go left, and then I'd go left, and then I'd end up here. And if that value is null, that means we never found the value and the value is not in the tree. So therefore, we are returning a null pointer. And if it returns null, that's our way of telling the user that the value that we're looking for here is not in the tree, and there's no reason to compare if the subtree is valid, because that means that we've already proven it's not a valid subtree because we have that value in tree T, but it doesn't exist in S at all. So here's what I want to do next. So here's the method. And then I have a case of 3 if-else statements. So what I'm going to do is we're making this decision. So if cur data is equal to value, then we just return that current pointer. I do want to point out again before we go any further, remember I mentioned on Wednesday, that when I was working with binary search trees that you're going to see we have to check for null all the time to prevent seg faults. When I do things like this, you're going to see this again when we go into lectures. It's the first thing I do is I consider all the possible scenarios where we might run into a null pointer and account for those first. In this case, I want to account for the fact that we got all the way down and we couldn't find anything else. So the current pointer is null. If I commented this out and I were to try to run this, I would definitely get seg faults. And the reason why is because we have child nodes that have null pointers. And eventually we would get here, and then we'd try to get the data from a non-existent data element. And that is how we get the segmentation fault. So to account for this, the very first thing I do is I make sure that I've checked for all the null possibilities. If the value is found, then we just return the current pointer. So the current pointer is what we've passed here. And then that's how we would return. Otherwise, the 2 else if statements, we are going to return first if cur data is greater than value. So if I'm currently at 10 and I want to see if 16's in the tree, then if cur data is greater than value, excuse me. So if I'm currently in a node with 10 and I'm trying to find 8, then value would be 8. And therefore I'd want to investigate the left pointer and then the value. Otherwise, I want to invest, it's not equal, it's not less than, so therefore it has to be, the value has to be greater than. So therefore, we're going to investigate the right pointer. So one of two things is either going to happen. We're either going to find a value we're going to find a node that contains the value, and we're going to return a pointer to the address on the data heap of that node, or we're going to return null. Which brings us to the second part in the actual algorithm, which I call run subtree, and that is in subtree.cpp. So in subtree.cpp, let me scroll up before all my tests. What I've done is I have two binary search trees that I'm calling by reference. And first thing I do is I print out tree 1 and tree 2. And you're going to see that, as we've done in lecture, that this overloaded operator is going to print out the in order, pre-order, post-order, and level order traversal of the binary search tree. So the first thing I do is I call the method getRoot that we've discussed, and that basically just returns the node root of right tree pointer. So that's tree 2. And then what I do is I call tree 1, and I call that method getNodeAtValue. So right tree pointer here, I get that data and I pass it through and I see if that node is in the binary search tree. So for the example, the root of that second tree is 4. So that data is what's passed. And then I get a pointer if we're able to find 4 in the binary search tree. If this subtree returns null, the first thing I do is I say right tree pointer's data is not in the tree and therefore not a valid subtree. Otherwise, I'm going to run my algorithm. I'm going to call what I call check subtree by passing those two pointers, right tree pointer and subtree root. And so what's going to happen is we're going to go here and I'm going to get the value from 4, and you're going to see that we're going to eventually return left subtree there, and I have that pointer and right pointer set up. So what I'm passing to this final algorithm are pointers to those node locations, and this allows us to be able to, this now allows us to be able to recursively determine if this subtree is equal to this subtree. All right, so does anybody have any questions before? Oh, we have a question in the chat. All right, chat. I'm going to quickly stop share. Okay, do you return 2 values in lines 312 and 317? All right, so let me go back to the share screen. All right, so that's in the binary search tree. All right, so I do not return 2 values. Thought I fixed that. I had that error before. All right, so what you're doing is you're passing 2 nodes and you're returning a binary search tree node pointer. All right, so let's see if this chat thing's actually going to cooperate with me. There we go. All right, so it is a recursive call. And before I do that, let me. $420. I thought I fixed that because hold on, just to prove it to you that I'm not losing my mind. See, there are outputs, so I know I had it working like 20 minutes ago before we started lecture. So I don't want to return that at all. That's the public version. Dr. Morrison also shows you how to troubleshoot compiler errors. Right, so we're going to fix that. So what was the other one? 420, 423. Oh, and I fixed those two things with the return type. So make clean, clear, make subtree. Okay, so yeah, I don't know why it reverted. I remember having that exact mistake before, but it's fixed. Okay, so let's go back to the actual slide. Go all the way back to where we were before. So here's check subtree. And this code is going to be recursive. And the thing with this is that we have to check to make sure the exact structure. And then once we check the structure, let's check the data. So the first thing I do, again, for safety, we always check null cases first, right? So we're going to see here that there's the null cases for safety. If we get to a specific node and both of the subtrees are null, then that's good. So right tree, left tree is equal to null and right tree is equal to null, we return true. If left tree is equal to null and right tree does not equal null, then we return false. Likewise, if right tree is equal to null and left tree does not equal null, we also return false. Yep. If one is null and the other is not, then we've proven they do not have the same structure, then it's an invalid subtree. The next thing we're going to do is we want to compare the data for each node. So we have left tree and right tree. And if we've gone through these three cases, then we know we have both nodes are not null. So what I have here is left tree data equals right tree data. And middle here, we're going to use that to check to see if the current data in the node happens to be true. The next thing I'm going to do is I'm going to recursively call check subtree to see if it's valid on the left. And I pass left tree, left node, left pointer, and right tree, left pointer. And then I do the same thing with the right. Finally, if all the checks are true, then it's a valid subtree. So we have to have all three of these checks pass in order to work. The left structure has to be correct, the right structure has to be correct, and the current nodes have to match. So now I have this end of the function where I print the final results. So I showed you this where I get the root and then I get the node value, and that returns, get node at value, so that returns a specific node pointer. And then what I do is this, my little trick is if subtree is equal to null, it's not in the tree, and then else what I do is I print tree2 is, and over here I print a valid tree subtree of tree1. And what happens is if it returns false, I just print the word not. In test 1, I have the tree that comes up and then we show that here we can see tree 1, tree 2, I insert the same, but tree 1 I start out with 6 and 8. And then when I insert 4 into tree 1, then I insert 4 into tree 2, then 1 into tree 1, 1 into tree 2, and then 5 into tree 1 and 5 into tree 2. So this test should pass true. I do the exact same thing here, but you'll also notice that I insert 0 at the end of tree 1. So I had that 4, 1, 5, but I'm also going to have a 0 over here. And we know from our discussion that we anticipate that test 2 should return false. And test 3 is a much bigger tree. This test is going to return true, and I'll show you the tree that we expect to come out for both of the trees in an animation in a moment. And so here I have, in order to figure out everything, I ran it, proved it. So here we have the in order, pre-order, post-order, and level order for tree 1 and for tree 2. And as we anticipate, tree 2 is a valid subtree of tree 1. For tree 2, we have all the order printouts. And as we anticipated, tree 2 is not a valid subtree of tree 1. So for tree 3, we see that tree 3 is rather large and tree 2 is rather large. So let me click through. And what I put in here, we see that this didn't work out. And now here's tree 3. So tree 3 on the left is this big tree. And the crucial thing is what we do is we go through and we find the value at the root of the right, which is 15. And then when we figure this out, we get a pointer to both of these, and then we recursively check all of them. They say 12, 12's great. Then we go 30, 20, 20, 22, 22, and go back up, 35, 35, 31, 31, and then we go all the way back up, and we see that this subtree that we found matches this tree. So we then correctly point out that tree 2 is a valid subtree of tree 1. Let me go back in the chat here. So in the chat, so from Chase says, how long do you think it would take to solve a problem like this in an interview? I had this same question on a HireVue interview last week, and they only gave me 10 minutes to code the solution. Needless to say, I missed this question. All right, so when I coded it up, just because of my experience, I was able to get it in under 10 minutes. The thing that I did was I drew it up. So I'm going to stop the share and so when I was doing this problem, the first thing I would do is I was thinking through it, and when we had the subtree, what I knew is I had to find the node first, right? So when you gain more experience programming, you'll get that experience with being able to program pre-order, in-order, post-order. So I was able to code that up and come up with the correct way. It was also beneficial for me because this binary search tree I've presented in lecture is a binary search tree that I've coded myself, so I know the code base very well. In these lead codes or interview or HireVue type interview questions, they typically give you a kind of a binary tree pointer, I think. In fact, let me look up, I'll quickly go through. So in this specific one that comes from, so here's subtree of another tree. What they will give you here, and actually let me go back to screen share so you all can see what I'm doing. It's taking its sweet time downloading. So in this case, is subtree, you're giving tree node S, right? Let me see what's going on in the chat. Yeah, they gave me a base node class with a struct predefined. So in this case, here they have the struct tree node, and you have left and right, and you have some sort of constructors. So here you recognize the member initialization lists. And then what we would be doing here is it a subtree? And at this point, the question is, we have to figure out where to begin. So the first thing you would do is you would come up with some sort of way of saying left and right. You would find where the subtree is, right? And you have to figure out where S is. So you would have some sort of way of saying, you'd have to figure out first where, if the current node is null, what are you going to do? So in this case, if you have to traverse the tree to find that specific value. Let me correct it. Traverse the tree. And then when you find it, recursively compare. So in these type of lead code questions, you can actually write another method, right? You're allowed to do that. it's just when they run their test that they're running on it, the is Subtree call is what's going to run off their test. So you can include other things in there to make it work. So if you have 10 minutes, the crucial thing is you think if you're drawing things out, you say, all right, well, I know that I have to be able to do this. And I would know if I'm trying to do, so for example, if I'm trying to do a pre-order traversal, then I would say void pre-order, right? And then just tree node S, right? So a tree node S, what's would happen is if, well, this would be printing it out, but we would be looking for some sort of value. In this case, it's an int val. And now what we're doing is we're trying to get the value. So we would be saying pre-order S, comma, val, because it has the value here as a member of the struct. So the reason why they're doing the struct is to try to help you do it faster, because if it was a class, you'd have to look up some sort of method. Whereas here you've accessed the value, and here you're saying if the value, if S val is less than value, that means that the value we're currently analyzing is less than the value, so you'd want to go right if we were trying to search. But here we would just go left, middle, right. So you have to come up with the approach, but if you understand what's going on here, that should help you out quite a bit. So let me go back to the chat. You're welcome. All right, so does anybody have any other questions? Yeah, my recommendation to all of you, for those of you who are still here, so let me stop the share. For those of you who are here, you have a really unique opportunity this semester. Usually there's about a month break, and this semester you're going to have a huge break. And my recommendation to you will be build on, do independent projects, and just practice these problems. Lead Code and HackerRank are tremendous resources for students to be able to practice these kind of things. And the more you practice, the better you get. And in your case, Chase, I'm impressed that you were able to make progress at all, considering we just started covering binary search trees. But with the more practice you get, and you've heard other students talk about how they've interviewed several times at a company. There's no shame in not doing well the first time. Everything is a repetition. It's you're not running. You're not going to bench your best possible weight the first time you do something. You're not going to run your best possible mile or do your best possible thing. So in this case, Chase, and this may not bring you much kind of comfort, but the best thing you can do is just keep practicing, because it's a problem that can be done relatively simply in 10 minutes the way they have it set up. It's just in this kind of environment in class, what I want to do is I want to help you not just understand how to program it, but actually how to think it through. What are we doing and why? Okay, so I want to analyze and do this with a recursive trace. Once you get more practice and you understand the data structures, then you will do well on the problem. Yeah, always. It's good. That's the right attitude. It's a good experience. All right, so does anybody have any other questions? All right, well, on that note, you all have a wonderful evening. It's 7 o'clock, and I will see you all tomorrow morning. How should we start some kinds of independent projects during the break? So with that's a good question. So for Jonathan and Fankong, I will be, starting next week, we're going to be doing the pre-turnship. And the pre-turnship is where you're going to have the opportunity to work with a mentor who's currently in industry. And you're going to independently develop a project. I'm going to teach you how to do research and actually propose an independent project. And companies really like students who take their own initiative to be able to develop an independent project. And the benefit of understanding data structures is that data structures, having that stronger computer science background, gives you a more informed ability to make better decisions about the project flow. So what I'm going to teach you over the next, so this is going to be week 9 starting next week. So the next 6 weeks, you're going to get a lot of instruction and practice on how to develop and implement independent projects. Did that address your question, Fankong? All right, are there any other questions? I'm looking forward to it. I think you all are going to really enjoy the pre-internship. I think it's going to be great. All right, well, if there are no other questions, then you all have a wonderful evening.